Polarization is a property of waves that can oscillate with more than one orientation. Electromagnetic waves such as light exhibit polarization, as do some other types of wave, such as gravitational waves. Sound waves in a gas or liquid do not exhibit polarization, since the oscillation is always in the direction the wave travels. In an electromagnetic wave, both the electric field and magnetic field are oscillating but in different directions. By convention, the polarization of light refers to the polarization of the electric field. Light, which can be approximated as a plane wave in free space or in an isotropic medium, propagates as a transverse wave. Both the electric and magnetic fields are perpendicular to the wave's direction of travel. The oscillation of these fields may be in a single direction, or the field may rotate at the optical frequency. In that case, the direction of the field's rotation, and thus the specified polarization, may be either clockwise or counterclockwise. This is referred to as the wave's chirality or handedness. However, there are important classes of materials classified as birefringent or optically active in which this is not the case, and a wave's polarization will generally be modified or will affect propagation through it. A polarizer is an optical filter that transmits only one polarization. Polarization is an important parameter in areas of science dealing with transverse wave propagation, such as optics, seismology, radio, and microwaves. Especially impacted are technologies such as lasers, wireless and optical fiber telecommunications, and radar. Introduction. Wave propagation and polarization. Most sources of light are classified as incoherent and unpolarized because they consist of a random mixture of waves having different spatial characteristics, frequencies, phases, and polarization states. However, for understanding electromagnetic waves and polarization in particular, it is easiest to just consider coherent plane waves. These are sinusoidal waves of one particular direction, frequency, phase, and polarization state, characterizing an optical system in relation to a plane wave with those given parameters can then be used to predict its response to a more general case. Since a wave with any specified spatial structure can be decomposed into a combination of plane waves, and incoherent states can be modeled stochastically as a weighted combination of such uncorrelated waves with some distribution of frequencies, phases, and polarizations. Transverse electromagnetic waves. Electromagnetic waves, traveling in free space or another homogeneous isotropic non-attenuating medium, are properly described as transverse waves, meaning that a plane wave's electric field vector E and magnetic field H are in directions perpendicular to the direction of wave propagation. E and H are also perpendicular to each other. Considering a monochromatic plane wave of optical frequency f, let us take the direction of propagation as the z-axis. Being a transverse wave, the E and H fields must then contain components only in the x and y directions, whereas Ez equals Hz equals 0. Using complex notation, we understand the instantaneous physical electric and magnetic fields to be given by the real parts of the complex quantities occurring in the following equations. As a function of time t and spatial position z, these complex fields can be written as, and where lambda n is the wavelength in the medium and t equals 1, f is the period of the wave. Here x, a, h, x, and higher complex numbers. In the second, more compact form, as these equations are customarily expressed, these factors are described using the wave number and angular frequency. In a more general formulation, with propagation not restricted to the plus z direction, then the spatial dependence kz is replaced by where is called the wave vector, the magnitude of which is the wave number. Thus the leading vectors E and H each contain up to two non-zero components describing the amplitude and phase of the wave's x and y polarization components. For a given medium with a characteristic impedance, H is related to E by, and, in a dielectric, eta is real and has the value eta 0, n, where n is the refractive index and eta 0 is the impedance of free space. The impedance will be complex in a conducting medium. Note that given that relationship, the dot products of E and H must be 0, indicating that these vectors are orthogonal, as expected. So knowing the propagation direction in eta, one can just as well specify the wave in terms of just x and a describing the electric field. The vector containing x and a is known as a Jones vector. In addition to specifying the polarization state of the wave, a general Jones vector also specifies the overall magnitude and phase of that wave. Specifically, the intensity of the light wave is proportional to the sum of the squared magnitudes of the two electric field components. However, the wave's state of polarization is only dependent on the ratio of a to x. So let us just consider waves whose x2 plus a2 equals 1. This happens to correspond to an intensity of about 0.00133 watts per square meter in free space. And since the absolute phase of a wave is unimportant in discussing its polarization state, let us stipulate that the phase of x is 0. In other words, x is a real number while a may be complex. Under these restrictions, x and a can be represented as follows, where the polarization state is now totally parameterized by the value of q and the relative phase. By convention, when one speaks of a wave's polarization, if not otherwise specified, reference is being made to the polarization of the electric field. The polarization of the magnetic field always follows that of the electric field, but with a 90-degree rotation, as detailed above. Non-transverse polarization. In addition to transverse waves, there are many wave motions where the oscillation is not limited to directions perpendicular to the direction of propagation. These cases are beyond the scope of the current article, which concentrates on transverse waves. However, one should be aware of cases where the polarization of a coherent wave cannot be described simply using a Jones vector, as we have just done. Just considering electromagnetic waves, we note that the preceding discussion strictly applies to plane waves in a homogeneous isotropic non-attenuating medium, whereas in an anisotropic medium the electric or magnetic field may have longitudinal as well as transverse components. In those cases, the electric displacement d and magnetic flux density b still obey the above geometry, but due to anisotropy in the electric susceptibility, now given by a tensor, the direction of E may differ from that of D. Even in isotropic media, so-called inhomogeneous waves can be launched into a medium whose refractive index has a significant imaginary part, such as metals. These fields are also not strictly transverse. Surface waves or waves propagating in a waveguide are generally not transverse waves, but might be described as an electric or magnetic transverse mode, or a hybrid mode. Even in free space, longitudinal field components can be generated in focal regions, where the plane wave approximation breaks down. An extreme example is radially or tangentially polarized light, at the focus of which the electric or magnetic field respectively is entirely longitudinal. For longitudinal waves such as sound waves in fluids, the direction of oscillation is by definition along the direction of travel, so the issue of polarization is not normally even mentioned. On the other hand, sound waves in a bulk solid can be transverse as well as longitudinal, for a total of 3 polarization components. In this case, the transverse polarization is associated with the direction of the shear stress and displacement in directions perpendicular to the propagation direction, while the longitudinal polarization describes compression of the solid and vibration along the direction of propagation. The differential propagation of transverse and longitudinal polarizations is important in seismology.